So we just saw that every adjunction gives rise to a monad, which made us a little bit awestruck that the universe is so nice. But it's even nicer than that. In fact, every monad comes from an adjunction. This is not at all obvious, right? So let's take a look. If I have a monad on some category C, and I have a monad on it, so that's in particular an endofunctor M, right? Then I would like to factor this as an adjunction. So I need to find some category and a functor going this way and a functor going that way, such that if I do this composition, then that should be the same as just doing the endofunctor. Right? So I know that if I start with such an adjunction, then I always get a monad. But now the claim is the other way around. If I start with a monad, I should find an adjunction like this, right? And in fact, there's many ways to do this. And one way to do it that we've seen before is to take this to be the Kleisli category of the monad M. And then in one of the now you try exercises, you defined a functor which embedded the original category into the Kleisli category. And here again, we could also define a kind of forgetful functor which forgets about the Kleisli structure. So remember that the Kleisli category here is the category where the objects are the same as this, but the morphisms are from A to B in the Kleisli category are the same as the morphisms from A to MB in the original category. Right? So we're thinking of these things as effectful functions, and there's a way to turn these things back into C again if you basically make everything effectful. So let's see if we can do this like this. So here first we need to define this forgetful functor, right? And if you remember the embedding like this, it's not doing anything on the objects, it's just embedding them. So if we want this composite to be the monad M, then we better apply the monad M here, right? Otherwise we're not going to get the right composite, because the other one is just the identity on object basically. So here I'm going to apply M to X. It's the monad apply. It's the same as the functor apply, but Agda doesn't know that. Okay, and then let's see. So here I'm basically saying that let's just make every object one of these effectful things, right? That's how you can turn effectful things into pure things. You just make everything effectful. What do we need here? Well, we have a Kleisli morphism F. So that's something from A to MB, right? And now we have to make something from MA to MB. But that's exactly what the bind is doing, right? It's upgrading A to MB to MA to MB. So let's use the bind of F, bind M of F, bind for the monad M, then that works, right? And the bind in turn, let's see if this loads now, yeah. The bind in turn we could define using the join and the functoriality of M. Okay, and then the identity follows exactly from the laws of the bind, which follows from the laws of the join and the return. So this is the bind return law, and here is the bind law for the morphisms. So that makes it a functor. And now let's see that we have an adjunction. This is actually really easy, because here we have now, see what we need. We have a Kleisli morphism from Mx to B, and we have to make a C morphism from X to MB. But the Kleisli morphism here goes into MB in the original category, right? Which is exactly what we have here. So we can just use the f itself. And similarly, going the other way, it's the same thing. These things are defined to be the same things now. So it's really easy to show that they are inverses because they are not doing anything. All the things that are happening are pushed around in the types. Naturality, which is usually quite easy to prove, is here a little bit more complicated to do. So I've done it for you so we don't have to spend time on it. Maybe there's a better way to factor this for the bind laws rather than the monad laws. I don't know. But again, there's not much happening. Basically what we're doing is, so this is what we want to prove equal to this. And we're just taking this thing, here we have a return before an f map. And we're just using naturality of return to push this return all the way to the right. So you can see here it's making its way here, and then it's moving left. And it's moving left, moving left, moving left until it hits this join and just becomes the identity. And that's what we wanted. So it looks like a lot, but it's actually not that much happening. It's just naturality of return all the way until and the return interacting with join at the end. And then I haven't proved it here, but you can see, and you can prove if you want, that if you now take this adjunction that we just constructed and construct a monad from it, then you recover the original monad M, right? Because this embedding does nothing on objects and this one is applying the M. And similarly, you have to use the laws a little bit to see that you get the right action on morphisms. But so this way you can see that every monad arises from an adjunction like this, which is unexpected if you ask me at least, but that's the way it is. So nature is amazing.